hard one. Okay, so tomorrow, I mean in the next lecture, I will complete the proof. Well, there will be always some gaps that I won't cover. I mean some theorems that come from singularity theory or from differential topology, that I will just recall them and use them, okay? But my intention is to give you an idea how is this theorem proves, okay? Well, so first of all, let's recall some results from differential topology. So the first result is Ehresman fibration theorem. Okay, so let f from E to B be a smooth function, smooth map between smooth manifolds. Okay. So if f is proper, this means that for every k inside B compact, the preimage is compact, and submersion, and this means that the derivative is surjective at every point of E. Then F is a locally trivial fibration. Okay, and what does this mean? So this means that for every U container in B simply connected, and any B, well, open here, open, and any B inside U, we have a trivialization. There exists a diffeomorphism so we have a diagram like this. Here we have F to U, F inverse of U, the diffeomorphism, and F inverse of B times U, and this is the second projection, and this commutes. Okay? Okay, this is Ehresman fibration theorem. Well, furthermore, if D is a closed submanifold, such that F restricted to D is also a submersion. And then F fibers E I don't know what's the word here. Locally, trivially, over D. And this means that the above diffeomorphism can be chosen to take F inverse of U intersected with D to F inverse of B intersected with D times U. Okay, so this theorem, we will just use it. Well, a consequence of this theorem is the following proposition that, first of all, I have to recall a definition. So definition, let A R S be topological spaces such that no, well, just this, the topological space. So a continuous function R from 0, 1 times S to S is called a retraction of S to R over A if 1, so at time 0 it is the identity, 2 at time 1 it is always inside R for every x in X, and R1x is equal to X for every X in R. So restricted to R is the identity. And 3, for every time R restricted to A is the identity. Okay. So using Ehresman's fibration theorem, we can prove the following proposition. So let F from E to B be a proper smooth map let C contained in B be the set of critical values So consider A contained in R, contained in S, contained in B, such that S intersect the critical points inside S are inside a relative interior of A inside S. Then every retraction of S to R over A can be lifted to a retraction of F inverse of S to F inverse of R over F inverse of A. Okay, so we can lift retractions under these conditions. Okay. Well, I won't prove this property. I will just use it. You can find this property in the proof in Hossein's book. Well, also he will use other theorems that are not in his book. So, but this is just a differential topology. Okay. So using these results, we will give a sketch of proof of a theorem that implies Lefschetz theorem. Okay. It's much general than this theorem of Lefschetz, and when we complete the proof, we will know how to compute this mu that appear in Lefschetz theorem, this mu of the middle relative homology. Okay, so let us state the theorem. So here, theorem. Okay, so let E be a compact complex manifold. This means that it's non-singular. D be a hypersurface, a device, be a submanifold, a smooth submanifold of codimension 1. Okay. And let F from E to P1 be a holomorphic function. Okay. So let's C equal to C1 CS contained in P1 be the set of critical values of F. And fix a point infinity in P1. Okay, that this might be equal to a critical value. This might be in C. Okay. So if F restricted to D has no critical values, in P1 minus infinity, and f restricted to E minus the fiber at infinity has only isolated singularities then hk of E minus the fiber at infinity and minus D relative to the fiber at any point B minus D is isomorphic to a free abelian group of finite rank for k equal to n and 0 otherwise. Okay, this is for every point B in P1 minus C and infinity. Okay, so we're saying that we have a one parameter family here, all right, such that at the critical values we will have singularities, right, of this family. We can remove one element of this family, infinity, that can be even singular, can be very singular. And if this family, after removing that point, satisfies that it only has isolated singularities, then we can compute the relative homology of the whole family minus the divisor relative to a smooth fiber minus its divisor. Okay. Okay. So a picture of this. The situation is something like this. So we have here, we have C. Here we have infinity. So here we have F. This is a regular value. This is B. And we have some critical values here, C1, C2. Maybe I should put it here. So here we will have fibers with singularities. Maybe with a lot of singularities, but just we need them isolated. And the other fibers are smooth. And here at the infinity, we might have something really weird, a lot of singularities, you know. But we don't care. And also we have a divisor here that is transversal to all fibers. D, okay, and D can intersect the infinity at a singularity. It doesn't matter. Okay. So we can compute the relative homology of the complement of D in the affine part less relative to a smooth fiber, the affine part of the smooth fiber. Okay, no questions? No? Okay, so I will start the proof, but I will finish it in the next class. Okay? So proof. So first of all, without loss of generality, we can assume that there exists some disk, delta disk, inside C, such that well, this happens. So we will have delta here. We have in the boundary we have B. So B belongs to the boundary of delta. And all the critical values are inside delta. And C is contained inside delta. So we might have here C1, C2, C3, C4. Okay? So this can be done after an automorphism of P1, right? We can assume this after an automorphism of P1. Okay? So okay, so now we will define di for every point ci in C. We will define di's as disk around each ci. So this will be d1, d2, d3, d4. So I take di, a disk centered at Ci in such that di bar is contained in delta and di bar is disjoint from dj bar. Okay, for I different from j. Okay, something like the picture. And we will connect each critical point with B by a path. Oof. So I take here something like this. This will be lambda 1, lambda 2, lambda 3, lambda 4. So I take write it just here, lambda I from 0, 1 to delta is a path connecting B with Ci, and they satisfy that lambda I intersected with lambda j is just the point B for I different from j. Okay?
Do you need extra condition over D or
No.
no?
No. It's just, no. It's the condition is that F restricted to D is a submersion.
Just one?
No. Yes. Yeah, just that. I mean, f restricted to D minus the fiber at infinity, it has to be a submersion. So it doesn't have any critical point inside D. Right? If you remove everything and you just leave D, and you remove also the point at infinity, f restricted to D is a submersion. It's a locally trivial fibration. You can apply Ehresman theory there, right? You are in the same situation as in Ehresman theory. Okay. Okay, so where is the proposition? I erased it. Yeah, I erased it. Well, okay, by the proposition the second proposition that I recalled, so we know that since, let's say, the union of from I1 to S of the di bar union with lambda I, this set is a contraction of the whole P1 minus the infinity, right? Equals C, right? We can use the previous theorem to conclude that the same happened in the fibration, right? So F inverse of this union is a contraction of F inverse of this, and this is E minus the fiber at infinity, right? Yeah, but well, I want to use it in the relative version. I mean, well, I have this minus the divisor in the fibration, and also I have this here, right? Okay, so in particular, the cohomology of this E minus the fiber at infinity and the divisor relative to the fiber at the regular point minus the divisor is isomorphic to HK of F inverse of this set relative to the regular fiber, right? See? Do you understand what is this? This is just this part here. This. This union. So certainly you can contract the whole plane to this set, right? Okay, so let S be defined as the following union: lambda I minus d I bar. Okay, so lambda S is just this union of this path until here, without this point. Right? It's open in this extreme. Okay. So, and S bar is, so since S bar can be contracted. I don't know if this is to the point B, right? We will have that, in fact, this HK of F inverse of the union of the DI bar union lambda I minus D relative to the regular fiber is isomorphic to HK of the same thing now relative to S bar. Right? Okay, and now we can cut out S by the excision property. And so we will have that this is in fact isomorphic to HK of F inverse of the union 1 to S. This is a disjoint union of the DI bar minus D relative to, so let's call this point, so this point here, let's use, here I will call it B1, B2, B3, B4. Okay, so it's relative to the fiber, the regular fiber at the union, well, the union from I1 to S of the regular fiber at BI minus D, where BI is lambda I intersected with the boundary of DI. Okay, well, we also assume that it intersects just in one point and we don't have problems. Okay. Okay, and so this is isomorphic to a sum, right? The sum from I equal to 1 to S of the homology of the preimage of DI minus D relative to the fiber at BI minus D. Right? Okay, so what's the situation now? So we have reduced the problem to a problem that is local around a critical value in P1, right? So now we just care about what is happening in a neighborhood of a critical value, right? So the picture that we care about now is something like this. So we have here, maybe I should I should erase somewhere. I don't want to. Okay, so we have here. We have here di. Here we have ci, and here we have bi, right? And upstairs we will have well, let's call that. So upstairs we will have here ci, that it's singular. We will have the other regular values. I mean the regular level sets, and we have the fiber at bi. Okay. So now we just care about what's happening here, right? Okay, so we will reduce it more to something also that is local upstairs, not only local downstairs. And here we have also the divisor d. Okay. Okay, now so for every ci in C, let pi contained in F inverse of ci be the set of critical points. Okay, so now for every point P in Pi, I will take a ball, consider a ball. So consider a closed ball, well, a ball B, BP, centered at P, well, such that for every pair of points in Pi, the BPs are disjoint. I mean, BP bar would be, let's say, Q bar is empty. Also, the ball doesn't intersect D. Also, F restricted to the boundary of BP intersected with the preimage of DI is a submersion. So we can do this always if we can reduce the radius of DI if necessary. Okay, so the picture is something like this. So let's do this big. So we have here the singular fiber. Okay. We have here the balls. We have one here, another one here, another one here. bigger. Okay, I have here the smooth fiber, and I have here the other regular fibers. So here I have the critical points, P1, P2, P3, and this downstairs we have CI, DI, and BI. Okay. So here the ball is not contained in the pre-image of DI, because otherwise here at this point it won't be a submersion. Right? So just this is why we shrink a little bit this disk. Okay. So now okay. So again, using the fibration given by Ehresman theorem, we can retract outside the balls. We can retract the fibration to just the regular fiber at BI outside the ball, and leaving everything inside the ball equal. I mean, at the, in the same way that it is right now. So we can retract this F inverse of DI minus D. And also we have here the divisor D, and we have it disjoint with all these balls. Okay, we can retract this to the union of the balls. So the union for P in Pi of the closed ball BP, and the regular fiber, so F inverse of BI minus D. Okay, it's something like moving everything there, but leaving the boundaries fixed. Okay, so we deduce from this that now this group is isomorphic to the sum of from I1 to S of HK of the union for P in Pi of BP bar union with F inverse of BI minus D relative to F inverse of BI minus D. Okay, and again by excision we can have, okay, here is excision. This is isomorphic to the following thing. So it will be the union for P in Pi of BP relative to the disjoint union. Well, this union is also disjoint. P in Pi of F inverse of BI intersected with the ball BP. Right? So it's just erasing everything and just taking the disjoint union of what is inside the ball and this part of the fiber, the ball and this part, the ball and this part. So again, this implies that this is now a direct sum I equal to from 1 to s and the direct sum of p in pi of hk of bp bar relative to f inverse of bi intersected with bp bar. Right, so now we are just in the local situation. I mean, we just have this situation. We have here the ball. Here we have, sorry. Here we have isolated just one critical point, P, and we have a regular fiber here and all the other fibers. And this is F. Right? Okay, so what is left now is to prove that in this situation, these homology groups are all 0, except for k equal to n, and for k equal to n, this is free of finite rank. Okay, so what I will do now is to prove this just for a special case. So now I will consider the case where P is a non-degenerate singularity. So let us consider the case where P is a non-degenerate singularity. Okay. So first of all, by Moore's lemma, we know that in a situable coordinate system, so in situable coordinates around P, so let's say P is the 0 of the coordinates, and let's say that the coordinates are z1 to zn. F is of the following way: f of c1 to cn is equal to f of P plus c1 squared until cn squared. Okay, so without loss of generality, assume that f of P is 0. Okay, so we will have this, right? So what we have to prove now, or what we have to compute now, is the relative homology for f given by this Moore's function, right? So is it clear? So for the Morse function, we will use the following lemma. Well, the lemma is what we want to prove. So let 0 less than rho less than epsilon squared be real numbers, such that and consider T the set of points in Cn such that the norm, like the real Euclidean norm, is less or equal than epsilon squared, and the Morse function is bounded by rho. Okay, so what is this? This is exactly BP. This is BP bar. Okay. This is the intersection of the ball with the pre-image of the function of some disk centered at 0. Right? 0 will be the critical value here. We're assuming that Ci is 0. Right? So we're in this situation here. So T will be the BP bar, and let F be the points in T such that the Morse function is exactly rho. So rho will be the regular value here, Bi. Bi will be rho. Ci will be 0. The regular fiber will be T. And the whole pre-image is F. No, the other side. I mean, the whole pre-image is T, and the regular fiber is F. Right? So what we want to compute is exactly the relative homology of T relative to F. Okay. So then the homology of T relative to F is isomorphic to Z if K is equal to N, and 0 if K is different from N. And furthermore, this Hn of Tf is generated by the real part of T. That's the generator. Okay, it's a real ball. I don't know what time is it. Just 1 second. Okay, so you don't have questions? No? Is it clear? If we prove this, we will prove the theorem in the particular case where all the critical values are non-degenerated. Right? Okay, so proof. Let sigma be the square root of epsilon squared minus rho over 2. So the first thing to note is that F is diffeomorphic to Q, that is the set of points UB in Rn times Rn, such that the norm of U is equal to 1, the norm of B is less or equal to 1, and U and B are orthogonal. Okay, and what is the diffeomorphism? Is just taking here Z equal to X plus I y, and you have to take it to x over the norm of x and y over sigma. Okay, so if we look at the equations, we see that so what does this equation mean? This equation means that the sum x1 squared minus y1 squared plus x2 squared minus y2 squared and so on is equal to rho, and x1 y1 plus x2 y2 plus xn yn is 0. Right? This is this equation here. Okay. And so if we have that z is in Cn, this property also holds, right? And this property means that the sum x1 squared plus xn squared plus y1 squared plus yn squared is less than or equal than epsilon squared, right? So if you replace this equation in the second equation, you will have that 2 times y1 squared up to yn squared is less than or equal than epsilon squared minus rho. So you divide by 2, take a square root, and you have this relation. The norm of y is less or equal than sigma. So y over sigma has norm less or equal than 1. Okay? And the inverse is easy to produce also. So this is diffeomorphism. Okay. And also it takes the real part of f. So what is the real part of f? The real part of f is the real points here in Rn such that they are inside the ball, and their sum is, well, their norm is exactly square root of rho. Square root of rho. Square root, right? So this is a sphere, right? This is an Sn minus 1. Okay. So it takes this sphere to the 0 section, let's say Q0. That is just the set of points U0 in Q, right? It just goes to the point that doesn't have any imaginary part, right? And this is a fibration, right? This is you have here a fibration over Sn minus 1, right? This thing, it's a fibration over, with the first coordinate, it's a fibration over Sn minus 1. And in fact, it is a sub-bundle of the tangent bundle of the sphere, right? You're taking the sphere, here the Sn minus 1. This is the 0 section. And at each tangent space, you're just taking a ball of radius 1 here, right? Something like that. Okay. So in particular, is Q can be contracted to the 0 section, right? So in particular, Q can be contracted to Q0. Right? Yes? And so the homology groups HK minus 1 of F, these are the same thing as the homology groups of Q and the same thing as the homology groups of the sphere, right? Right, and this is Z for K equal to 1 and N, and 0 otherwise. Right? Okay, on the other hand, it's easy to see that we can contract T to 0, to the region, right? T is contractible. It's kind of a ball, right? And so now taking the exact sequence, the long exact sequence, of the pair TF, we will get that HK of TF. So here we have HK of F, HK minus 1 of T, and here we have HK of T. So these are 0 for K bigger than 1, K different from 1, right? So we have an isomorphism here for K different from 1. So different from 1 and different from 0 also, right? So we're almost done. I mean, we already proved that the Hn of this thing is Z. In fact, the isomorphism here is the boundary map, right? So we know that the generator here is exactly the class of Sn minus 1. That is the real part of F, right? And it comes from the real part of T. The real part of T will have the boundary, its boundary will be the real part of F. So the generator here is the real part of T in Hn. And all the others are 0. The only one that we are left to prove is that for K equal 1 and K equal 0, they are 0. But so what happens with H1? H1 of TF. So here we have 0. And then we have here H0 of F, H0 of T, and H0 TF and 0. But this map is an isomorphism because both are connected, right? In particular, this one is 0 and this one is also 0. Okay, and so we are done. So is it clear? No?
Repeat that the real part of F induce the generator to the...
I mean, so So the real part of F, we know that goes to Q0, right? Q0 is the zero section of Q, right? And it is isomorphic to an S in n-1, right? So here, when we take the n-1 homological group, the isomorphism will take the, I mean, what will be the generator here? Will be, well, it will be Sn-1, right? And here in the contraction, it will be also Sn-1. I mean, the Sn-1 embedded inside Q. That is the Q0, right? And the Q0 comes from the real part of F, right? And the real part of F is the boundary of the real part of T, right? If you restrict T, you will see that T is a ball, a real ball. And its boundary is F. I mean, it's this real part of F. And it's of dimension n. And it will be the generator here in Hn, right? Okay, so corollary of what we already did is that in the same context of the theorem, the theorem is true if all singularities of F restricted to E minus the fiber at infinity and the divisor are non-degenerated. Okay, so we prove it in this case. We have proved this. Okay. So with this, I can prove a version of Lefschetz theorem just with this. So a consequence of this corollary is the following. So let me check the time. Okay. So first of all, let's define definition. So let X be a smooth projective variety of dimension n. So fix an embedding X inside Pn. Okay. So we say that a pencil of hyperplane sections so it's a map, it's a rational map F from X to P1, okay, determined by a line P1 inside the dual projective space of Pn, the dual space of Pn. What does this mean? This means that for every t in P1, the preimage of t is x intersected with some ht, where ht in the dual projective space is the hyperplane corresponding to t in the line P1, and the map F is not defined over this x prime, that it is x intersected with, let's say, h0 and h infinity. I mean, you can take any two hyperplanes and intersect them, and you will see that all the intersections of all hyperplanes, they will be intersecting in x prime. Okay, it's not defined here. This is the base of the pencil. Okay, and so this is something like you have here. Okay, you have something like this. Right, so this is x. This point here is x prime. Here you have h0, h infinity, and so other. So a pencil is like a family of hyperplanes varying in one parameter. Right, so this intersection is like a Pn minus 1. We say that a pencil of hyperplane sections of x is a Lefschetz pencil if for every t in P1, xt, that it is defined to be as the fiber of t equal to x intersected with ht, if xt is a smooth hyperplane section or for almost all TNT, well, it's smooth upper plane section, or it only has a non-degenerate one non-degenerate singularity and f from x minus x prime to p1 has only a finite set of critical values. Well, this is like saying that it has a regular value. I mean, this is what I want to say. And if has a finite set of critical values, critical point. In particular, they are isolated. Okay. So Lefschetz pencil is something like that. I mean, you take the sections. Each time that you're taking a section, the section is smooth, and whenever it's tangent, so it appears some singularity, it will just appear one singularity, and it will be a non-degenerate singularity. It will be a good singularity. Okay, these are Lefschetz pencils. So from what we have done, we can prove like a weaker version of Lefschetz theorem. So theorem. So this is, let's say, weak Lefschetz. Well, it's not that weak. So let X be a smooth projective variety of dimension n, and let y and z smooth hyperplane sections intersecting each other transversely, and such that there exists some k in n such that y minus k z is the principal divisor of some f for some f from x to p1, a Lefschetz pencil okay. Here I put the fiber at 0 is y, the fiber at infinity z. Then the homology of x minus z relative to y minus y intersected with z is isomorphic to c mu if k is equal to n, and 0 if k is different from n. Okay, so this is almost Lefschetz theorem, but we're assuming that the two hyperplane sections belong to the system generated by this Lefschetz pencil. Okay, and so proof of this. Okay, so So we have this situation, right? We have here x. Here we have a hyperplane section y equal to f to the fiber at 0. Here we have z, the fiber at infinity. And here we have some other fibers, right? Here we may have a singular fiber that has only one singularity and is non-degenerated. So let's say f1 of critical value, and some other fibers, right? So a regular fiber. And here we have x prime, right? Here we have this map that is f, that is the pencil that goes to P1, and it's not defined here in x prime. Okay, so we will take the blow up. So let's x tilde be the blow up of x along x prime. So we will get something like this. So the x tilde will be here. We will have this blow up, right? This will be a divisor d that is isomorphic to x prime times P1, and we will separate all the hyperplane sections, right? Here we have y, here we will have z, and we will have the other fibers, the critical one, the singular one, and the other, right? And here we can define this map f tilde that is well defined here, right? And this is the blow up. Okay. Okay, so well, now we are almost done. We have constructed this f tilde that satisfies all the hypotheses that we needed in order to apply the previous theorem. Also, we know that all the critical points that will appear in f tilde will be non-degenerated because they will correspond to, whenever we remove the divisor, we will just have to look at the singularities of the hyperplane sections appearing in the Lefschetz pencil, and they by definition are non-degenerated, right? So from the corollary, we know that. So by the corollary, we know that hk of what? So it will be x tilde minus f tilde, the fiber at infinity, union the divisor, relative to a regular fiber, right? So the fiber at 0 minus the divisor. This is isomorphic to z mu if k is n and 0 otherwise. Right, but what is this? X tilde minus the fiber at infinity union d. So this is x tilde minus d, right? Minus f tilde at infinity, and f tilde at infinity is just this guy, right? This is f tilde at 0, right? So this is isomorphic under the blow up to x minus Z. Right? And the other part is just f tilde, the fiber of f tilde at 0 minus d, that is just isomorphic to y minus y intersected with z. And so it's proved. It's proved. Okay, so we're done. So what we have proved is that if we add this restriction that the divisor is a principal divisor of a Lefschetz pencil, then we have proved the theorem. And well, the point is that this kind of always happen. I mean, it's the most likely thing to happen. I mean, Lefschetz pencils are dense in the space of all pencils that you can take. Right, this is an exercise. Well, it's not that easy, but also it's not that hard. Of an algebraic geometry course. Okay. So just I will put this remark here. So remark, a general pencil is a Lefschetz pencil. So even if we don't have this property, I mean, if we take, I mean, now Lefschetz theorem is true if we take y and z general hyperplane sections, right? But in fact, it is true just taking two smooth hyperplane sections, satisfying this property, and this might not be a Lefschetz pencil. This is something that we will prove in the next class. Okay, and also a bad part of this is that how do we compute mu? We have to compute the set of critical points in a Lefschetz pencil, and all that we did is non-constructive. We haven't constructed this pencil explicitly, so we don't have any way to know how many critical points it has. So we cannot compute mu in this way. You see? And also the proof of this, as you can imagine, is just to prove that the set of pencils that are not Lefschetz pencils are a Zariski closed subset of a proper Zariski closed subset of the dual of X inside Pn dual, right? So well, no, it's the dual effect. But it's just to proving that there is the bad pencils are inside some algebraic variety, and so we are also not producing a Lefschetz pencil. We're just proving that it exists. Okay, so in next class we will give some ideas of how we can compute this mu when we take one pencil, an explicit pencil, and it's not probably a Lefschetz pencil. Okay. So.